Decorator pattern to add memoization to recursive algorithms in Python. Thought for a second. Here is your same structured beginner-friendly content for Decorator pattern to add memoization to recursive algorithms in Python introduction. Recursive algorithms are elegant and easy to write for problems like Fibonacci numbers, factorial, climbing stairs, dynamic programming problems, tree and graph traversal problems. However, recursion often has a major problem. The same subproblem gets solved many times. This leads to repeated calculations, slow performance, exponential time complexity in some problems. To solve this, we use memoization. And in Python, one clean way to add memoization is with the decorator pattern. This approach is useful because it allows us to improve recursive functions without changing core logic, reuse memoization for many functions, separate optimization from business logic. Understanding this topic helps learners understand recursion optimization, decorators in Python, caching techniques, dynamic programming ideas. What is memoization? Memoization is an optimization technique where we store the result of a function call and reuse it later when the same input appears again. In simple terms, memoization equals save previous results so we do not recalculate them. Example concept. F5. Calculated once means stored, means reused next time. Why recursive algorithms need memoization. Many recursive algorithms solve the same subproblems again and again. For example, Fibonacci, fib, calls, fib4, fib3, and fib4 again calls fib3. So fib3 is calculated multiple times.
Example concept.
Repeated subproblems means repeated work, means slow execution. Memoization avoids this repetition. What is the decorator pattern? A decorator in Python is a function that wraps another function to extend or modify its behavior. In simple terms, decorator equals a wrapper that adds extra functionality to a function. Example concept. Original function means wrapped by decorator, means enhanced function. This is useful because the original recursive logic stays clean. Why use a decorator for memoization? Without a decorator, you may add cache logic directly inside every recursive function. That makes code repetitive, harder to read, less reusable. With a decorator, memoization logic is written once. It can be reused for many functions. Recursive function remains simple. Example concept. Memoization logic separated from recursive logic. Basic recursive Fibonacci without memoization. Def fib n. If n equals to 1, return n. Return fib n minus 1 plus fib n minus 2. This is simple but inefficient. For larger n, it becomes very slow. Example concept. Simple recursion means elegant but slow. Idea of memoization with cache. We use a dictionary to store results. Example. Cache equals cache. When function is called, check if input already exists in cache. If yes, return cached result. Otherwise, calculate, store, and return. Example concept. Check. Cache means use saved result if available. Basic memoization decorator in Python. Def memoize func. Cache equals cache. Def wrapper n. If n in cache, return cache n. Result equals func n. Cache n equals result. Return wrapper. This decorator stores results in cache. Using the decorator at memoize def fib n. If n equals 1, return n. Return fib n minus 1 plus fib n minus 2. Now, fib is automatically memoized. Example concept. At memoize means recursive function becomes optimized. Full working example. Def memoize func. Cache equals r. Def wrapper n. If n in cache, return cache n. Result equals func n. Cache n equals result. Return wrapper. At memoize def fib n. If n equals 1, return n. Return fib n minus 1 plus fib n minus 2. Print fib 10. Print fib 30. #fast because of memoization. How this works. Step 1. Decorator creates cache. Cache equals 0. This dictionary stores already computed values. Step 2. Function call goes to wrapper. When we call fib10, Python actually calls the wrapper. Step 3. Check cache first. If n in cache, return cache n. If result already exists, reuse it. Step 4. Compute only if needed. Result equals func n, cache n equals result. This stores the result for future use. Example concept. First call computes means, later calls reuse. Why this helps recursive functions. Recursive functions often revisit the same arguments. Memoization changes the process from repeated recalculation. Calculate once means reuse many times. This can drastically improve performance. Fibonacci example with memoization. 4. Fib 5. Without memoization, Fib 3 and Fib 2 are recalculated multiple times. With memoization, each value is computed once. Example concept. Fib 0, Fib 1, Fib 2, Fib 3, Fib 4, Fib 5 means each only once. Time complexity improvement without memoization. Fibonacci recursion can take 2 to the n10 because of repeated branching. With memoization, each value is computed once. On. This is a huge improvement. Limitation of the basic decorator. The earlier decorator only works for functions with one argument. Def wrapper n.
But many recursive functions need
Multiple arguments, keyword arguments. So, we need a more flexible version. Improved generic memoization decorator, def memoize, func, cache equals def wrapper. If args in cache, return cache args. Result equals func args. Cache args equals result, return result. Return wrapper. Now it works for any number of positional arguments. Example with climbing stairs. At memoize def climb n. If n equals 2, return n. Return climb n-1 plus climb n-2. Print climb 10. This uses the same decorator without rewriting memoization logic. Example concept. One decorator means reusable across many recursive problems. Example with 2 arguments. Suppose we solve grid paths. At memoize def grid paths RC. If R is equal to 1 or C is equal to 1, return 1. Return grid paths R-1C plus grid paths RC-1. Print grid paths 3. This works because the cache key is RC using functools.wraps. A better decorator should preserve function metadata like function name docstring. We can do that using functools.wraps. From functools import racks. Def memoize cache equals cache. At wraps func def wrapper star args. If args in cache, return cache of args. Result equals function args. Cache args equals result. Return wrapper. This is a more professional implementation. Complete improved version from functools import wraps. Def memoize func cache equals $. At wraps func def wrapper x args. If args in cache, return cache args. Result equals func args. Cache args equals result. Return wrapper. At memoize def fib n. If n is equal to 1, return n return fib n-1 plus fib n-2. At memoize def grid paths RC. If R equals 1 or C equals 1, return 1. Return grid paths R-1 C plus grid paths RC-1. Print fib 30. Print grid paths 4. Memoization versus dynamic programming. Memoization is closely related to dynamic programming. Memoization top-down, recursion-based compute only when needed. Tabulation, bottom-up iterative fill table, step by step. Example concept. Memoization equals top-down DP using cache. Built-in Python option. LRU cache. Python already provides built-in memoization. From functools import LRU cache. Example. From functools import LRU cache. LRU cache, max size equals none, def fib n. If n equals 1, return n minus 1, plus fib n minus 2. Print fib 30. This is often the easiest and best practical solution. Why build your own decorator then? Building your own memoization decorator helps you understand how decorators work, how caching works internally, how recursion is optimized. Example concept. Custom decorator means better learning. Built-in decorator means better convenience. Advantages of decorator-based memoization. Advantages include clean separation of logic, reusable optimization, faster recursive execution, easy to apply with @memoize. Example concept. Same recursive code plus decorator equals optimized solution. Limitations. Challenges include cache keys must be hashable. Memory usage increases, may not work directly with mutable arguments like lists. Example concept. More speed means more memory used. Common mistakes. Using mutable arguments as cache keys. This causes errors because lists cannot be dictionary keys. For getting recursive calls, use decorated version. In Python, decorated recursive calls point back to the wrapped function, which is what we want. Assuming memoization helps every recursion. Memoization is most useful when there are repeated subproblems. It is less useful when every recursive call is unique. Example concept. Memoization works best with overlapping subproblems. Concepts learned from this topic. Understanding decorator-based memoization helps learners understand ACK, recursion optimization, ACK, Python decorators, ACK, caching with dictionaries, ACK, overlapping subproblems, ACK, dynamic programming ideas. This topic is very important for writing fast recursive solutions in Python. Simple definition. Decorator pattern for memoization. A Python decorator that adds caching to a recursive function, so repeated calls with the same input return saved results instead of recalculating. Final summary. Memoization is a powerful technique for optimizing recursive algorithms by storing previously computed results. Using the decorator pattern in Python allows us to add memoization cleanly without changing the core recursive logic. This makes recursive code faster, cleaner, more reusable. A custom @memoize decorator is a great way to understand how caching works, while Python's built-in @LRU cache is a practical production-ready solution. Understanding this topic is essential for learning Python decorators, recursion optimization, and dynamic programming.